Hello, my name is Greg Thane. I'm a core HTCondor developer here at the Center for High Throughput Computing at the University of Wisconsin-Madison. And this talk is about how to run multi-core jobs on multi-core machines, or more generally, how to run jobs with different amounts of CPU cores, memory, disk, and other resources on machines in your, or really, what happens when individual machines in your cluster seem to have as many or even more computing resources that an entire cluster did just a decade ago. As an example, Intel is now shipping single processors with over 100 threads on each processor, with high-end systems even having more than one of these processors per machine. So this problem is real and getting more urgent day by day. For the rest of this talk, I'll be using my desktop for all the examples. This machine is a bit older with just 8 cores and 16 gigabytes of RAM. But that does mean that all the code snippets and output that I'll show you on these slides will fit on one screen. More importantly, most all of these examples are screenshots from working HTCondor installations. So what does Condor give us out of the box on this 8-core, 16 gigabyte machine? The Condor Start key will, by default, create one slot per core and divide up all the other resources like memory, disk, maybe GPUs, evenly into each of these slots. In this case, that results in 8 slots with about 2 gigabytes of memory, subject to rounding, in each slot. But that is just the default. There are worker node configurations that let the administrator change the number and size of each of these slots. Perhaps you don't want HTCondor to use all the cores in the machine, but you'd like to save a couple for some other, maybe non-Condor use. In that case, you could set the num CPUs knob to 6, and there would be 2 free cores on a machine like this. Same holds true for memory and disk. But if you don't know how much memory any given machine has, there is a parameter, reserved_memory, which tells Condor how much memory not to include after it's detected all the memory. This can be handy when you don't know how much memory a given machine has. And while most of the rest of this talk is about what you can do, quick word on maybe what you should do. A lot of people think that the best way to make their codes go fast is to make each job use all the cores it detects on whatever machine it lands on. But that's not really the HTCondor way. If you have a choice, we would prefer that you run single core jobs if possible, because you probably care not just about how long your code runs on any one machine. You probably care more about how much time your job spends idle waiting to get to run on any machine. And the more cores you request, generally speaking, the longer your job waits idle in the scheduler's queue. But sometimes you just don't have a choice. It may be difficult to reorganize your work into smaller jobs, or maybe you don't even have access to the source code or the ability to change the way jobs work. So the rest of the talk is for those cases where you just need more cores or memory and can't adjust the size of your workflow. So assuming the default configuration for HTCondor on this machine, remember that we get 8 single core slots, or places where a job can run. Given that, and a job submit file that looks like this, and remember now, always include the request CPUs, memory, and disk line in your Condor submit file. Where could a 2 CPU job run? And assuming we submit this, and there are no 2 core slots available on the machine, well, in that case, sadly, HTCondor will find no matching slots for your job. And as a result, the job will remain idle in the scheduler's queue forever. The Condor Q-Analyze tool will tell you that there are no matching slots for this job, even though there may be plenty of idle cores. So the immediate reaction of some users might be to lie to HTCondor and change the submit file so that only requests 1 CPU core, even if that job spawns 2 threads or processes when it runs. And should this happen, well, the job will start running, but HTCondor, assuming it has root leaf privileges and running on Linux, will limit the usage of the job to just 1 core by using the cgroups mechanism on Linux. If the job tries to use more memory than requested, the system will evict the job and may even put it on hold. One way to think about this is that Condor has partitioned the job and jailed off all the other resources from its use. When this happens, the job will either go on hold, or it may run much, much slower by trying to use more resources than it has access to. Our solution to this problem is to create a new kind of slot, which we call a partitionable slot. Actually, we have two new kinds of slots, partitionable and dynamic. We now call the original, old kind of slots static slots. There is usually one partitionable slot per machine in the typical configuration, but it is never claimed or runs jobs directly. The size of this slot varies over time. It holds all the unused resources. Partitionable slots are not on in Condor by default, but the configuration snippet below for the worker node will enable P-slots on this machine. Note that this requires a restart of the start daemon in order for it to take effect. And once we change this configuration and restart, Condor status will now show this output. Note that instead of 8 individual slots, we now have just one slot with about 16 gigabytes of memory. We call this the partitionable or P slot. Running Condor status to show some additional slot add attributes reveals that this slot has the attribute named slot type with the value partitionable, and it holds all 8 cores in addition to the almost 16 gigabytes of memory that we just saw. With this new configuration, if we submit the same job as before, the one that did not match to any slots and stayed idle forever, and maybe another one, an even larger job now with 3 cores, we can see that jobs like this will start and will run. Remember, the P slot will create dynamic slots to run each of these jobs with enough memory for each of them. The dynamic slots are named with the slot name of the P slot, followed by an underscore, and a unique number. In rare circumstances, you can configure a single machine to have more than one P slot, which is why the D slots have the names they do, but we won't cover that configuration today. It's highly unusual. We still have the unclaimed partitionable slot holding any number of unnamed resources. And note that each D slot has a different amount of memory, depending on how much memory each job that it's running in requires. Just to be sure, if we rerun the Condor status command that we ran before, we see that the slot type attribute of the newly created slot is named dynamic, and the memory remaining in the partitionable slot has been diminished by the amount in all the dynamic slots. And let's say that the job in dynamic slot 1_2 exits, and the claim can't be reused. The resources that were in that D slot, including CPU cores, memory, disk, and any custom machine resources, are then returned to the parent P slot, where they can be reused again for some other job. Now, while partitionable slots solve a lot of problems, especially if an admin or user cannot predict the workload beforehand, sadly, they do not solve all scheduling problems. One particularly thorny problem remains: starvation. To illustrate, assume that I have the same 8-core machine and submit 8 single-core jobs. As you might expect, all 8 jobs should match and consume the whole machine. All is fine so far. Note that because the partitionable slot always exists, Condor status shows there are 9 total slots. This may throw off some monitoring scripts or maybe some humans, so it is something to always be on the lookout for. On the other hand, if there were a single 8-core dynamic slot running an 8-core job, Condor status would only show 2 slots, even though the machine is full. Because of this, when P slots are configured, it isn't useful to count total number of slots in your pool anymore. So this is something to be aware of. But getting back to the original problem, assuming that we have this machine that's running 8 single-core jobs, and then I submit my 2-core job that could run the machine when idle. When can this 2-core job run? Well, if 2 or more of the single-core jobs exit at the same time, then maybe the 2-core job could run. But if there's an infinite or maybe very large supply of single-core jobs, then the 2-core job will never start. We call this problem starvation. HTCondor's usual user priority scheme does not help us in this case, because the user priority, the owner of the running single-core jobs, will continue to get worse and worse, and the owner of the 2-core job should at some time have a better priority. However, HTCondor only takes user priority into account for jobs that match slots. And because the 2-core job will never match a 2-core slot, the user priority will not help us. So this is still a problem. Now, this problem is a fundamental scheduling problem. and as such, there is no simple solution that is correct for all cases and conditions. At the heart of the problem is a fundamental tension between fairness and throughput. On one end of the spectrum, if all we care about is throughput and we don't care about fairness at all, we could do nothing. As long as our machines are full, we have good throughput, and if a 2-core job has to wait forever, so be it. But on the other end of the spectrum, the moment that 2-core job appears, we could potentially preempt any running 1-core jobs in order to make space for it. This preemption would interrupt a job in the middle of its run and create badput, which can be a problem for another reason. So when we think about scheduling and how to do this, we should always first think about what policy we want and measure the performance of how we're doing, because ultimately something has to give. And here at the CHTC at the University of Wisconsin, we spend a good amount of time thinking about how these things work. First, we collect a lot of data about job sizes, why machines are idle, how much badput there is, and graph them. And here's the important part. We look at these graphs every day to make sure that we're thinking about our policies and our policies are doing what we expect them to. We strongly recommend to most large sites they do the same. Measure your badput and look at it every day. Another approach, which can work well in certain circumstances, is what I call steering computation. And the idea behind steering is that if you have a lot of machines and you don't want holes or unused capacity on each machine. Also, this tends to work best when you have a very limited number of different sizes of jobs, ideally just 2 sizes, each of which can completely fill a machine. The trick here is that you basically line up all of your machines by some arbitrary criteria, maybe by an integral machine number or a rack number or something like that. Then you try and pack all of your jobs of one type to the left side of this virtual line and all the jobs of the other type to the right. This way, there are only holes in the middle, and you can densely pack jobs of each type to each side. Several large Condor sites use this mechanism in practice today with great success. The implementation in HTCondor configuration is pretty straightforward to do this. Each machine needs to advertise its position in the line. Here I'm calling it longitude and making it a floating point number, but you could make it anything you want. You need to put this attribute in the startee attrs on each worker node and then run reconfigure. Then, in the negotiators configuration, sort each machine that matches your candidate job with the negotiator pre-job rank expression. Like the above, rerun Condor reconfig on the negotiator, and that's all you need to do. As a short aside, if you don't know what the negotiator pre-job rank attribute does, or how to configure the negotiator, or what one is, we have a whole talk on this subject targeted towards HTCondor administrators who want to know more about scheduling configuration. This talk is up on YouTube on the Center for High Throughput Computing's channel, and we highly recommend it. Another potential solution to this problem is to dedicate one or more machines to only running the big jobs for, some definition of big. When there are no big jobs, then you just let this machine sit idle. While this may sound inefficient in many cases, if there's only one such big machine, maybe it's a machine with a lot of memory or GPU or something like that, letting it be idle, not running any jobs may be acceptable. This may be especially true if this machine was purchased for the dedicated reason of running these large jobs. Both previous solutions, sorting and reserving, are sort of niche solutions. Most admins with partitionable slots and a non-uniform workload are going to want to have some kind of system based on draining. To illustrate this, let's return to our 8-core machine and assume that it's running 3 jobs that consume all the CPUs in the box, as the Condor status output shows. HTCondor comes with a Condor drain command. This takes, as an argument, the name of the worker node to start draining. When it is run, the partitionable slot immediately goes into the drained state. As is common, this is a poor naming choice on the part of the HTCondor development team. The name really should be draining, as the slot hasn't completed the process yet, but is still in the process of draining the machines. Because of backward compatibility, we are uneasy about changing this confusing name. Note that you need HTCondor administrative privileges in order to initiate draining, and depending on the security setup of the pool, you may need to run the drain command from the central manager machine. When a partitionable slot is drained, by which we mean draining, and in the drained state, no new jobs will start on it, even when there are idle resources. And this is the key point about draining. And how does this work? In a very typical way for the HTCondor system, when a P-slot is in the drained state, the requirements expression is temporarily set to a new value, whose default is false. This way, matchmaking is stopped, Condor Q-analyze shows the correct results, and so on. This drained state is all in memory, or what we call soft state in the Condor start date. So, if the machine or the daemon is restarted, when it comes back, it will completely forget that it was in the drained state and restore normally in the unclaimed state. Draining can be canceled with the Condor drain-cancel command. After this, the P-slot will return to the unclaimed state, and the jobs will continue running as usual, and no new matches can be made. The start expression of these slots is returned to their original value. This can be very handy when admin wants to drain down a machine until a certain number of resources are available, and then return the machine to normal operation. Once draining has started, the machine will stay in the ill-named drain state until the drain-cancel command is issued, unless the option -resume on complete is set, in which case, when the very last dynamic slot exits, the P-slot will go back into the unclaimed state again automatically. This behavior of staying in the drain state may be useful for an administrator who wants to gracefully take a machine down for an upgrade or reprovisioning of the hardware. The jobs in the dynamic slots will either run to completion or run until the number of seconds in the max job retirement time attribute have expired. Again, the negotiator talk on YouTube discusses this max job retirement time knob. This knob may be the most important, yet most underutilized knob in all of HTCondor, and we recommend that you set this to some pool appropriate value or expression. If you have been paying particularly close attention, you may have noticed that I said that when a P-slot is drained, by default, requirements expression goes to false. And with so many things, too many things, it often seems, in HTCondor, this too is configurable. If you specify -start and some expression on the Condor drain command line, this is the expression that the P-slot switches to. This is very useful for backfilling jobs, which you hope to be short-running, on draining machines, maybe to eke out some additional extra throughput during the draining process. In such a case, if you submit a job that matches those requirements, perhaps the requirement has some special custom class-add attribute to only match special backfillable jobs, Condor status will look like this. The P-slot is in the drained state. The draining D-slots are in the claimed retiring state, but the backfillable job is in the claimed busy state. This is the same state that a static slot would be when running a normal job. This is really advanced kind of configuration when you want to keep your throughput as high as possible, but it is possible to backfill jobs in a draining machine on Condor. Running the Condor drain command may seem like a manual process that may be tedious and prone to error, and you'd be right. HTCondor ships with a simple daemon called the Defrag daemon, which can automatically run Condor drain and Condor drain-cancel, and pick machines to run the drain command against and decide when to cancel the draining. This Defrag daemon is pretty simple. In particular, it never looks at the demand of jobs in the schedule. Rather, it just looks at the start Ds. With a couple of simple throttles, like defrag draining machines per hour, the Defrag daemon will try and keep some small number of start Ds always draining. Now, this may not be perfect for your pool, but it does get the job done, and most sites that have partitionable slots run some kind of defrag daemon. Maybe they run this defrag daemon that ships with Condor, or maybe they have a custom Python script that knows a little bit more about their policies and does a little bit more intelligent job of training. With that, I'd like to thank you for listening to this talk, and I hope that you've learned a little something about how to run multi-core jobs on Condor. If you have any questions, first, please check out our manual. It's at htcondor.readthedocs.io. Or, if you'd like to talk to a human, we have a good mailing list called HTCondor users that you can subscribe to at this link below. It's not very high traffic, but the questions that are on there are high value. And I would encourage anyone in the Condor community to subscribe to this. Thank you again, and I hope you have a great day.